Okay, anyhow, so announcements. Lab 3 is up. That's due next week on Friday. We have the prelim this Thursday, so in 2 days in the evening, 7:30 to 9:30 p.m. That's right here, 203 Phillips. Per our vote in a previous lecture, the rules are you can bring one 8.5 by 11 sheet of paper. You can put on it whatever you want. You can, typeset it, LaTeX it, make really fine print. What do you want to do? It's one sheet of paper, one letter-sized sheet of paper. You can do whatever you want with it. So those are the rules. I sent this out in an email. They had the coverage and everything too. We have all the past prelims up. We now have solutions for all the past prelims up as well. So that's there for you. So in some past years there were 2 prelims in the semester. In some past years there was 1 prelim over the course of the semester. This year we have 1 prelim total. So for all the past years where there was 1 prelim, I posted that 1 prelim. For all the years where there was 2 prelims, I posted only the first of the 2. That's because I looked at the second prelim, and it was like 2 years where this happened, where we had 2 prelims. In one case, like every part of every question would be like an illegal question for this exam. Like it covers stuff that we've not covered yet, or at least is not covered on the prelim. For the other of the 2 prelim 2s, there was like 2 true-false questions that I guess would be legitimate questions for this exam, and like the rest of it is all stuff that comes later. So I chose not to post those. I think it might cause more confusion than clarity. It just kind of muddies the waters on what's covered and what's not. So anyway, those exams are obviously out in the wild. I mean, if you know someone who took the class prior years, you can get a hold of them. Just trust me when I say that's not going to be useful. Okay, those exams are covering stuff we haven't covered yet. So I wouldn't even bother with them. I would focus on the ones that we've posted. One thing I neglected to mention in the email is that I do plan to have an extra question for the 5670 students on the prelim compared to the 4670 students. Okay, so the exams will not be quite the same. The 5670 exam will have 1 extra problem compared to the 4670 exam. Okay? Yeah. All right, any questions? Yeah.
Did you say there's 1 prelim this semester?
There's 1 prelim this semester, that's right.
Yeah, but the prelim schedule has 2. The official
Yeah,
qual.
I thought there was 2.
But there's definitely 1 because it's on the syllabus.
Yeah, so the way the prelim schedule is generated by the provost office, they tend to use like prior years, they just kind of replicate what you had the semester before, which creates all kinds of trouble actually, because it's even worse if you want to add a prelim. Like the students say, we'd rather have 2 prelims so we don't have so much of our grade riding on 1, and then you get like 1 slot, and then you're going to try to add 1 after the fact. So in this case, I deleted 1 prelim just because I felt like last semester especially, the schedule was just way too packed. So I deleted the second one, but we're still kind of allocated this slot if we want it by the provost office. But ultimately what's binding is like this sheet, the course policy sheet. That's what we're going by. So yeah, there's just 1 prelim total, the one we have on Thursday. That's it. Sorry? Midterm? What do you mean?
There's a 1 prelim. Never mind.
I always called them, in my undergraduate institution, we always called them midterms. Prelim was not a defined term. When I went to graduate school, prelim was the oral exam you took to determine whether you proceed in the PhD program or not. It was like the Weeder oral exam that all the PhD students took, the preliminary exam. So I read at Cornell, and it's like prelim is just this evening exam that you have, a midterm basically. It was odd terminology, but I've never heard anyone here question it. But you're questioning it? You'd rather call it a midterm?
Because there's only 1.
Oh, you have 2. It's a prelim. But I mean, prelim, I guess in this context, prelim would just mean preliminary to the final, right? So couldn't you have 2 preliminary exams to the final? I don't know. Who knows? We can. There's like an online, you can actually ask Uncle Ezra or something, this kind of stuff, where are these terms. While we're at it, we can ask why East Avenue is named East Avenue, right? All right. Okay, other questions? We're good? Okay. So remember, this is not covered on the prelim, what we're doing today. What we're doing on Thursday is not covered on the prelim. I guess what we did last Thursday is also not covered on the prelim, right? But this stuff's really critical for the labs. Okay, so the last lecture was pretty much what you need to do, what you need in order to do lab 3. what we're talking about here today, Thursday, and next week is like what you need to do lab 4. Okay, so this is important material, although it's, you know, it's not really important for the prelim or midterm or whatever we want to call it. Okay, so let me recap where we were. So we're talking about how to communicate over various channels, and we start with simple channel models and then kind of add complexity gradually. So we eliminated ISI to begin with and just studied how to communicate over channels that didn't have ISI, and I think we have a pretty good, at least preliminary handle on how to do that. We'll loop back to it later when we talk about coding, error correction, and so on, but we have a reasonably good handle, at least, you know, how to start the problem without ISI. And the question we're looking at now is how do you deal with ISI? Okay, so suppose you have a channel matrix of the form y equals hx plus z. H is not diagonal, so that therefore you have ISI by definition. So how do you contend with that? Okay, how do you encode your bits into x so you can decode them easily in y? Okay, so last time we noted that for arbitrary h, like any h you've got here, you can eliminate the ISI from it using the SVD. Okay, so just write h out as its SVD, singular value decomposition, kind of absorb the two change of bases into x and y respectively, and you're left with a diagonal matrix left. So that's a channel with no ISI. Okay, so any channel with ISI can be reduced to a channel without ISI by just doing an SVD. Okay, and I say just doing an SVD because conceptually, like, there's not a lot to that. You just like change the basis, both sides, you're done. In practice, though, that's not necessarily feasible, as we discussed. Okay, SVD is computationally expensive, so you can't do it very fast. You can't do it if the sequence lengths, you know, the vector sizes are long. Moreover, it requires quite a bit of knowledge about what the channel is, what h is at the encoder, so it can do the right change of basis. We talked about why that's a problem in practice and so on. Okay, so that was a good starting point. That's not the way, and that is what we'll do for lab 3, just to kind of get our feet wet. That's not the way people proceed in practice, though. So in practice, you use the structure of H. So H in practice is not some arbitrary matrix. It's like a Toeplitz matrix, and you exploit that structure. Okay, so to explain this, I'd like to do the circulant case first. So suppose a channel is y equals hx plus z, and H is circulant. Okay, in real life it's not circulant, it's Toeplitz, but we'll, you know, bridge that river when we get to it. So let's assume for starters that H is circulant. Of course, we'll assume it's known. So how you deal with the fact that H is unknown in practice, we'll table for now. We'll also table the synchronization issues as well. So H is a known circulant matrix, and Z is our usual IID Gaussian noise. So how do we communicate over a channel like this? Okay, power constraint. I always forget the power constraint because we have a power constraint on X to boot. Okay, so how do you communicate over this channel? So one approach is to try to diagonalize it, akin to what we did with the SVD for regular channels. So take H. If H is circulant, then we know we can write it as W lambda W Hermitian. W is the IDFT matrix. Lambda is this particular diagonal matrix. It's got the scaling factor, and it's got the impulse response of H, i.e. the leftmost column, DFT of that along the diagonal. Okay? So that's always true. For every circulant matrix, I can write it like that. Okay, and then I can use that fact as follows. So just write H out as its eigenvector, eigenvalue decomposition. So I just plugged in for H here. I haven't done anything else. All right, then at the decoder side, if you imagine taking the DFT of Y, okay, so you receive this vector Y, this is a wave file, right? So you receive this wave file. Take the DFT of the wave file, that's this, right? DFT is by definition W Hermitian times Y, so W Hermitian times all this. The W Hermitian W's cancel. W Hermitian Z is the DFT of Z, right? So I get the DFT of the noise. W Hermitian X is the DFT of X. So if I just switch everything to the frequency domain, input and output, I end up with a channel like that. Okay, so if I view at the encoder side, if I view the input as not X, but the DFT of X, and at the decoder side, if I view the output of the channel not as Y, the time domain signal, but the DFT of Y, okay, then my end-to-end channel from the frequency domain version of X to the frequency domain version of Y, okay, that has no ISI in it, right? It's a diagonal channel matrix. Do you have a question?
Yeah, notation question.
Yeah.
In lambda, are the arrows on top of the H's supposed to be going leftward?
Yes.
Okay.
Yes. Because think of it this way. So when you multiply by a vector like this. You're doing a circular convolution between x and the impulse response of h. So that's equivalent to taking the DFT of x, multiplying by the channel gain, right? And then taking the IDFT. Okay, so what you want here should really be the DFT of the impulse response. So if this is the impulse response, then you want the DFT of that, and the notation in this class is just switch the arrows going the other way. So this vector is not the same as this vector. This one's the DFT of this one. Yeah. Transfer function was the term I was looking for. It's a transfer function. Okay, other questions? All right, so it's pretty slick. I mean, you just switch to the DFT domain, and suddenly your ISI is gone. Okay, and qualitatively what's happening is that a linear time invariant system can sort of smear energy from one sample to another in the time domain. It can, like, energy in one sample can kind of bleed into other samples in the time domain, because, you know, when you convolve something, I mean, you kind of spread the energy out, right? So that's ISI. Okay, and what the math here is saying is that in the frequency domain, that does not happen. If you have an LTI system, it cannot take energy in one sample in the frequency domain and then spread it out into multiple samples. Energy does not bleed from one frequency to another as it passes through an LTI system. Okay, if you have time variation, it can. If you have nonlinearities, it can. For an LTI system, energy cannot bleed from one frequency into another. Okay, so if that's a problem for you, this bleeding, okay, which it is for us, that's ISI. Okay, that makes our life hard, that makes our life complicated. Then just switch to the frequency domain, and that doesn't happen anymore. Okay, so far so good, but this kind of opens a whole can of worms here. So the various complications that we have to deal with. So, you know, yes, the ISI is gone, but we've created a bunch of other problems, like our input to the channel, which we now want to view as x left arrow, the DFT version of x. That's complex, right? So I want to encode the bits in a complex vector. So how do I do that? I'll just say how to do PAM over complex samples. Like when we talked about antipodal, on-off keying, and everything, you know, all that was for real samples, encoding bits in real samples. Now it's complex. How does that change the story? 2, what about the noise? In particular, what is the distribution of the noise? You know, Z was IID Gaussian, the original Z. I've taken the DFT of it. That's the noise I'm experiencing now, is the DFT of the original noise. So what's happening there? If I view the DFT of X as the input to the channel, and my encoder is encoding its bits in this object, I need to encode the bits in such a way that the inverse DFT of it, the time domain X, is purely real. Right? Ultimately, the input to the channel is a real vector. Right? That's sort of implicit in here. I didn't really write it down, but like x needs to be real here. Right? It's almost goes without saying. Right? It's like, you know, for ComCloud, you know, you specify a sequence of real valued samples. You can't really tell it like it's sample 3, send this complex number. It doesn't know what that means. In fact, it's meaningless. Right? Okay. So the input in time domain has to be real. So that's kind of an obvious constraint until you get to here. And here maybe it's not so obvious, because now it's like you're viewing the DFT version of X as the channel input, the effective channel input. So when you do that, you can't just choose this X arbitrarily. You've got to do it in such a way that when you take the inverse DFT, you get something purely real that you can transmit. So how to choose the DFT of X to ensure that the time domain version of X is purely real. And then lastly, there's the power constraint. So how do you choose the DFT version of X to ensure the time domain version of X satisfies the power constraint? Okay, so both issues 3 and 4 kind of boil down to the fact that we sort of know how to solve the problem if you had no SI, and your channel input was viewed as that, the time domain version of X. Okay, we've eliminated the ISI, but now our input is really viewed as this. So how do constraints on this, namely with the power constraint and the fact that it's purely real or needs to be purely real, how do those manifest themselves on this, which is what I'm now viewing as the channel input? Okay? Put with me? Okay. So we'll answer all of these. They're all posed as questions, I guess. I can put question marks here, right? They're all how to. Well, everything except the distribution of the noise. They're all questions. So we'll answer all 4 of these questions. We'll probably do it. Hopefully, we'll do it all today. And then we'll understand how to communicate over circulant channels. And then we just got to bridge the gap from circulant to Toeplitz. Then we'll be in pretty good shape. We're obviously not done then. You know, in reality, you don't know H exactly. You got synchronization. Okay, there are other things to worry about, but we'll be well on our way. All right, so I'm going to answer these 4 questions. We'll do it in reverse order, actually, because they kind of get easier as you move down. So we'll start with 4 and then work our way up. Okay? Okay, so let's start with the power constraint. So the power constraint we're given is on the time domain version of X. That's our power constraint. And the question is, how do I express this in terms of the DFT of X? Okay, it turns out we can relate the power in X time domain to the power in X frequency domain, and we don't need the expectation to do it even. So like the energy in the time domain X, this is X transpose X, right? Since X is real, transpose, I can replace with Hermitian, right? Since X is real. Because if X was complex, you would just write this as this. Okay, you'd skip that intermediate step. But X is real, so we get this is defined to be this. But then since it's real, I can replace transpose with Hermitian. And then let me just slip a W, what do I want? W Hermitian inside here. So that's identity, right? This part's identity, so it's doing nothing. Okay, and then I can write this as Wx Hermitian, right? No, not that, sorry. I can write this as W Hermitian X Hermitian times W Hermitian X, right? And this is the DFT of X, Hermitian, DFT of X. And that's what we define to be the energy in the DFT. Okay? So bottom line, energy in the time domain signal is the same as the energy in the frequency domain signal. Okay, the DFT is energy preserving. Okay, so there's no conversion factor there. The conversion factor is just 1. Okay, so that's quite convenient then. So our original power constraint we can just replace with the constraint that the energy, or the time average, ensemble average power in the DFT of X is at most P. Okay, so the power constraint we had on this X, we just replace it with the power constraint on the X we're actually working with, and that's that. Okay, so that was not hard. Let's keep going. This will get more involved as we step through these issues. So let's do 3. So we need to ensure that the time domain X is purely real, right? Okay. So the encoder is going to encode its bits into this DFT of X, and then you'll take the inverse DFT and then send that into the channel. Okay, so we got to make sure you choose this vector in such a way that when you take the inverse DFT, you get something purely real. So that raises the question, well, what constraints does one impose on this vector to ensure the time domain signal is purely real? So this is just like a fact about the DFT you've probably seen before. So the time domain signal is purely real if and only if the time domain signal is like not skew, it's conjugate symmetric about the mid frequency. Okay, so DC is real. Okay, sorry, this is frequency domain. The zero sample of the frequency domain, that's the DC, that's real. And then for every other sample except the 0th one, xk is x star n minus k for all k in 1 up to n minus 1. Okay, so DC is purely real, and then the whole rest of the spectrum is like a flip conjugate copy of itself. Okay, so you've probably seen this doing labs 1 and 2, right? I mean, you take a real signal, you take the DFT in MATLAB, FFT in MATLAB, right? And it's got like, one shape, concatenated with itself, right? Half the spectrum is redundant. Okay, here's a quick quiz. I don't do clickers, but here's a candidate clicker question. So if n is even, then there is an n over 2 sample, right? It would be a sample corresponding to this number. What can we say about that sample if the time domain signal is real? It's real. Right? This is true for all k. So if n is even, I can choose k to be n over 2. And then I get x frequency domain n over 2 equals x frequency domain star n over 2. Right? So it's real, just like the way the DC is real. Okay? Obviously, if n is odd, then there's no n over 2 sample, and that doesn't happen. OK. So one thing you can do is just like bake these conditions into your encoder. So you just say, OK, I'm going to do PAM to encode my bits in the frequency domain, and I'm going to do it in such a way that the x that emerges out of the encoder has this property. Okay, and then I take the inverse DFT, I'll get something purely real, I'll be good to go. Okay, that's one approach. That's perfectly legitimate. Okay, I can tell you it's kind of inconvenient though to be carrying these conditions around for the rest of our lives. Okay, like forever after, whenever we talk about x, we're gonna have to note that these conditions have to be satisfied when you pick x. Turns out to be a lot easier to just kind of make this automatic in the following way. Okay, so suppose n is even. Let's do the even case first. Okay, then the time domain signal can be written as follows. You have the DC. You have a bunch of samples I'm going to call x1. Okay, you have the n over 2 sample. Okay, and then all the rest of the samples here are going to be x1 conjugate flipped. I'm going to use MATLAB notation here. I'll write flip x1 star like that. Okay, if the time domain signal is real, then the frequency domain signal needs to satisfy this condition. Okay, that means I can decompose it as follows. You have the DC, you have n over 2. Those are two special samples. Okay, for all the other ones, they're just going to be flipped copies of each other. So by flip, I mean, you take the vector and the last entry becomes the first one and vice versa. Just flip it like that. Okay, so flip it, take the complex conjugate of these samples, and you'll get those samples. Okay? Any x that satisfies these conditions must look like this if n is even. Okay? If n is odd, you just don't have the n over 2 sample. So you still have DC. You have this vector I'm going to call x1, and then you just skip the n over 2 and just cut right to the flip thing. Like that. Okay? So what we're going to do, there are a few ways of approaching this. Like I said, you can view this as the whole input. Like the encoder should take the bits and then spit out a vector like this. Then you got to keep track of these constraints. This got to be real. This needs to be flipped conjugate copy of this, and so on. Okay, a much easier approach is just view x1 as the effective input to the channel. So view that. As the effective input. Okay, and if your encoder spits out this, you know what should be here, right? So like think of it as almost being part of the IDFT. Rather than having the encoder spit out this and then take the IDFT and send it, think of the encoder as spitting out this, okay? And then before taking the IDFT, you pad it out. Take this with the flipped conjugate version, okay? You got to specify a DC and an n over 2 sample. Okay, in practice, you just zero those out. So just require this to be 0, require this to be 0. Okay, you can motivate that in a few ways. One is, even if you allow the encoder to pick this entire thing here, it's probably not going to put any energy here or here. Okay, because when you do your bit power allocation procedure, remember that? Okay, it's going to tell you not to put energy here or here, usually. Okay, in practice. Most channels do not pass DC. Okay, the COM cloud does not really pass DC. Okay, so you put energy there, and the channel's going to eat it. So it's pointless. Okay, you better put your energy in here, around 7 kilohertz where it actually passes it. Okay. Likewise, this is really high frequency. Here it's, the Nyquist rate basically. Most channels don't have a real high gain near the Nyquist rate, so certainly ComCloud doesn't. So you're not really losing much by just zeroing that out, not even allowing the encoder to put energy there. Okay. Even if your channel did pass this with a reasonable strength, usually n is big enough that the loss you incur by just zeroing things out is not really that big. You're losing 2 samples out of n, right? So not that big of a deal. Here, in the n odd case, we view this as the input. And then before you take the IDFT, pad it with a 0. Take the flipped conjugate copy of the samples that came out of the encoder, put it here, take the IDFT of that. Okay? So the beauty of that is that the encoder can be oblivious. Okay, the encoder does not need to keep track of these conditions. Right? When you're mapping bits to samples, you don't even have to think about this. Because this is sort of unconstrained, right? This x1 does not need to have any particular conjugate symmetry to it, right? That's kind of automatic, right? So for the purposes of designing the encoder, you can just encode the bits right in x1 without even thinking about this kind of constraint over here. It just happens automatically. Okay, so we're going to view x1 as the effective input now from here on out. Okay, how you map x1 to the actual channel input depends on whether n is even or odd. In the even case, you're padding with 2 zeros. In the odd case, you're padding with just 1. We got to be careful about the power constraint, right? If I'm choosing x1 now, if I view this as the input, then I want to have the power constraint on this. I don't want to have to kind of like backtrack a power constraint from this one to this one. I want to do it once and then just keep track of a power constraint on x1. So let's think about this. So I have those intermediate samples, x1, I have the overall DFT x. How are these energies related? Sorry? No? How does this relate to this? Yeah. Right? Like that. Okay, if I just sum up, so this quantity here is the sum of the squared moduli, okay, of x. Okay, and we're zeroing these out. Okay, so you're going to get that norm squared plus that norm squared. But the conjugate doesn't change the norm, and flipping certainly doesn't change the norm, right? Okay, so this norm is this one plus this one, which is twice that one. Okay. Okay, so the power constraint in terms of x1 is just that twice twice the power of x1 needs to be less than or equal to p. Before I had the power in x had to be less than p. Now it's just replace this for this. Okay? And I personally find it helpful to think about it this way. Write it as 1 over n divided by 2. It's the same thing, right? Why do you think I like to think about it that way? This is more of a psychological question than a math question, right? Mathematically, this is the same as this. Like, there's no difference, so you never talk about why you prefer one over the other. It's the same quantity. Okay, psychologically, they're slightly different, right? This is a bit suggestive of something.
So when you have half the samples.
Sorry?
So when you have half the.
Yeah, I wouldn't say so that you have half the samples. You do have half the samples, right? So, I mean, when you think about a power constraint like this, I mean, the reason we call this power to begin with, let's do frequency domain. The reason we call this a power constraint to begin with is like that's the energy in the signal divided by the time, right? The time duration, right? Or maybe it's easier to think about it this way. It's like in the time domain, right? This is the energy in the signal, and that's the elapsed time. So that's power, okay? So here, x1 has about n over 2 samples. Okay, it's not quite because of the DC and so on, but when n is large, okay, close enough. It's about n over 2 samples. Okay, so this constraint is saying that the average power in x1 needs to be p. Okay, so this 2 is in some sense just normalizing, so you're dividing by the number of samples in x1 as opposed to by the number of samples in x. Good. Okay, so that's 3. Any questions so far? Let's do 2. What's question 2? The noise, right? Okay, if you had to guess what the distribution is going to be, what would you guess? And don't think about it hard. You're thinking about it too hard. Blurt it out. Sorry? Gaussian, yeah? IAD, Gaussian. Mean? 0. Variance? N, yeah. Seems like a reasonable guess, right? The noise in this class is essentially always IAD, Gaussian, 0 mean, variance N. Is that plausible here? Because what one means by plausible. I guess it's plausible in that, like, every other time noise has come up in a calm situation in this class before, it's been that. Okay, but we're talking about the distribution of this, right? Can that be IAD Gaussian? Can it be Gaussian?
Yes, I mean, the DFT of Gaussian, the Gaussian.
Well, I mean, when we say this, we mean a random variable with that density, right? Can the components of this have this density?
No,
Why not?
they're not real.
They're not real, right? I've taken IID Gaussian sequence in the time domain. I've taken the DFT of it. The DFT is in general going to be complex, right? So my noise is now complex valued, right? So, you know, any hope that we had this would be IID Gaussian is like immediately out the window, okay? Certainly cannot be IID Gaussian with this density. That would mandate that this was real. That would only happen if the time domain noise had the, you know, the conjugate symmetry that we just talked about, okay? And with probability 1, that is not going to happen, okay? Nonetheless, it is close to being this, okay? So we'll modify our definition of Gaussianity a bit, okay? And we'll make this work, okay? So it's not far off, okay? But it's important to recognize right off the bat, it's not going to be the usual IID Gaussian noise we've been dealing with up to this point, okay? It's going to be a more complicated thing. Okay. So on some level, like complex valued random variables are like a novel object unto themselves, right? In your probability classes, random process classes, you probably never had a complex random variable before, right? Have you? Anyone? 411? No? Yeah. So on some level you can say, whoa, this is a whole new world. You know, let's like revisit like all of probability theory now with doing things complex instead of real, right? I mean, it might seem to call for that kind of level of, you know, revisiting this material. On some level, though, it's really nothing new because, you know, a complex valued random variable just has a real part and an imaginary part, each of which are real valued, right? So a complex valued random variable you can think of as nothing more than a real valued random vector with two components to it, the real and the imaginary. Okay, so if you can deal with random vectors, real valued random vectors, you can deal with complex valued random variables. Just treat the imaginary and the real parts as like two components in a vector, and that's it. Okay, so we don't really revisit anything probability theory wise. Okay, we can just rely on working with random vectors to handle this. Okay, but the question arises, what distribution does this particular complex random vector have? Okay, so I'll show you the definition, and then we'll relate the definition to the random variable in question. Okay, so a random variable z. I'm going to do it in the random variable case first. We'll talk about random vectors in a bit. Random variable z. Here's the terminology we use. It's a real mouthful. Okay, it's circularly symmetric. Complex Gaussian. With variance n. All that's the defined phrase, okay? And we abbreviate this. Naturally, you want an abbreviation for this, okay, because it's a real mouthful. So we abbreviate it like this. It's like the usual script n with a c in front for complex Gaussian or circularly Gaussian or whatever. Anyway, Cn. Okay, if, so the condition is that the two components, the real part and the imaginary part, they need to be IID, regular Gaussian, so real valued Gaussian, with zero mean and variance n over 2. Okay? So again, think of a complex valued random variable as a random vector with two components. And we'll say that the complex random variable z is circularly symmetric complex Gaussian with variance n. Okay, if those two components, namely the real part and the imaginary part, are just IID regular Gaussian. Okay, no, this is not a circular definition. It has the word circular in it, but it's not a circular definition, and that we're not defining this in terms of itself. We're defining this new object in terms of one we already know. Okay? So there's no logical problem here. All right, let me point out a few things. Okay, so number one, why the term circularly symmetric? Why would you attach that particular name to this distribution? Okay, the reason is we'll show in a future homework. We don't have a homework for a while yet, but in some future homework we will show that if Z is circularly symmetric complex Gaussian and theta is some deterministic number and real, then e to the j theta has the same distribution as, e to the j theta z has the same distribution as z itself. Okay? People know what I mean when I write this d equals? Yes? No? No? Okay. So it just means the distribution is the same. Okay, so like if x and y are IAD Bernoulli half, then the distribution of x is the same as the distribution of y, right? They're both Bernoulli half. So it's fair to write this. They have the same distribution. Distribution of that equals distribution of that. Okay, but observe the chance that they are equal to each other is actually a half, right? The chance that this value equals this value is a half, but this distribution is the same as this distribution, right? Okay. Okay, so the claim is this is a random variable here, right? I have a random variable, I multiply it by some constant, I get a new random variable. Okay? Claim is that new random variable so derived has the same distribution as the original one. Okay? And what happens when you take, if you want to think about it in terms of densities, so imagine kind of the multivariate density over R2. Okay, so it's like a bell curve but in 2 dimensions. That's basically what you have here, right? Real and imaginary part are IAD Gaussian. Okay? When you multiply by this phasor, okay, you end up taking the distribution in the complex plane and rotating it by theta. Okay? So what this claims is that the distribution does not change when you rotate it. The distribution is circularly symmetric. So when you rotate it by theta, you're left with the same thing. Okay? Hence the name. Okay? Sometimes people actually define it this way. They'll define it as a Gaussian, a complex random variable whose imaginary and real components are jointly Gaussian with this property. Okay, and then it's kind of patently obvious why you would call it circularly symmetric. The issue is that this property is kind of useful to have, but often when you want to calculate stuff, you want to know the actual joint distribution between the real and imaginary parts. So I find it easier to define it in terms of that. They're IAD. All right, note the mean is just fixed to be 0. I didn't say with mean, mu and variance n. The mean is just locked to be 0. Okay, you cannot write Cn mu or Cn1 n. Okay, that's a syntax error. Okay, that's not allowed. It's got to be 0. Okay, and the reason is because of this circular symmetry that we want. Maybe my note should have a different numbering scheme from the questions. We have 4 questions and 3 notes, and I don't want them to get confused. So I'm going to label these as, this is A, and this one is B, just so we don't confuse. Maybe it's too late, but try to avoid confusion between the notes and the questions. Okay, why mean 0? Okay, the reason is if Z had mean mu that was not 0, okay, then when you go to look at the phasor shifted version of it, you're going to look at that. What would the mean of this be? That, right? That's not mu in general, unless theta is some multiple of 2 pi, right? Okay, so if you want circular symmetry, you can't have a non-zero mean, which kind of makes sense. If the distribution's not centered on 0, okay, then when you apply the circular shift, the mean turns around, okay? And so if you want circular symmetry, the mean has got to be locked at 0. There's no other possibility. So in our definition, we just lock it at 0. Last question, why n over 2? Okay, so in the definition, I say z is Cn0n if the real and imaginary components are IID, Gaussian, zero mean variance n over 2. Why do I put this 2 here? People see the 2? Is my water in the way? Okay, so the reason is as follows. It so happens that we tend to consider this quantity a lot. Okay, just trust me. Okay, this quantity will come up frequently when you're dealing with these circularly symmetric complex Gaussian random variables. Okay, so if you expand this out, this is real part of z plus imaginary part of z times real part of z minus imaginary part of z. Right? It's z times z star, right? So z star. Expand all this. The cross terms will cancel, right? And j. Missing the j, yeah. We're going to get 0. This is not what I wanted. Thank you. Missing the j's. So z is real part of z plus j imaginary. Z star is real part minus j imaginary. Okay, so now when I expand it, the cross terms cancel. I'm going to get the variance, i.e. the second moment of the real part. And then I have minus j squared. That gives me a plus variance, i.e. second moment of the imaginary part. This is n over 2, so n. Okay? So if you don't put the 2 here, if you just say real and imaginary part are IID, zero mean variance n, then you're going to get a 2 over there. Then this quantity here would be 2n. Okay? So you pick up the 2 one way or the other. So it's just a choice. Okay, you can embed it there, in which case you get clean n right there. Or you can define it with an n, in which case you're going to get 2n every time you do that calculation. All right, we're going to embed the 2 here, so we get clean second moments for z. Okay? Okay, that ends the notes. Let's return now to the distribution of the DFT of the time domain noise. So we noted this cannot be IID regular Gaussian, right? It's complex for starters, so no good. Okay. Here's like the next best thing. Okay, so this is a very nice distribution to work with. It's got lots of independence. This is a more plausible possibility for the distribution of z left arrow, right? So here's the question. Do we think do we think z left arrow is IID circularly symmetric Gaussian zero mean variance n? Can we hope for that? Got to have a conjecture first before you can start proving things. So we need a conjecture for the distribution of z. So should that be our conjecture? What do you think? Yeah? Yeah? Let me pose a question to you. Let's think in terms of degrees of freedom. So the original vector here, the time domain one, has, in some very intuitive sense, don't try to pin me down on this, it has like little n degrees of freedom, right? It's like little n independent numbers, right? One for each component, okay? If I had a random vector that was length n, IID with this distribution, how many degrees of freedom do I have? Like 2n, right? You have like n components, and then you got the real and imaginary part in each one, right? Okay, now, maybe you'd say, well, the variances somehow line up or something, but, this is actually a sign of a problem. Okay, there aren't really enough degrees of freedom to get all that independence. And actually, if you think about it this way, there's actually an easy way of seeing why this can't possibly be true. Z cannot possibly have IID components. This Z cannot possibly be IID across the components. Why not? Yeah.
If all the real were 0, then it would have to be imaginary.
If all the real were 0, it would have to be imaginary.
To preserve the power.
To preserve the power. Let's think on a realization by realization basis. So the power is like an expectation notion when you're talking about noise, right? So I have the discrete time noise sequence. I take the DFT of it. Do you expect all the samples to be independent of each other? Just in MATLAB, you just do like IAD Gaussian sequence, take the DFT. You're going to get n complex samples. Are they all independent of each other? Yes.
Well, the DFT, like a single element of the DFT of the Z depends on every single element of the other version.
Yeah.
So they wouldn't be independent.
Okay. By that reasoning, though, remember when I had IAD Z, and when we did the SVD, we end up looking at a quantity like this, where this is not a sparse matrix, not a diagonal matrix, right? It's an orthogonal matrix, right? So you get another Z vector, each component of which depends on like all the Z components, right? Yet somehow this ended up being IAD Gaussian as well, right? So somehow, even though each sample here is a function of all of them, because it's like an orthogonal change of basis, it's just kind of doing some kind of rotation, and it sort of preserves the independence across the samples. So maybe that happens here too. DFT is, it's unitary. Okay. This is my last attempt. Okay. I take IID sequence of Gaussian random variables in MATLAB. I take the DFT of it, I plot it. What's it going to look like? Yeah. It's going to be symmetric, right? The time domain signal is real, right? So I take the DFT, I've got conjugate symmetry, right? So there's no way the elements of this are IID. In fact, the second half of the spectrum is a copy, it's a flipped conjugate of the first half, right? This is what I was getting at with the degrees of freedom, actually, right? If you kind of count up degrees of freedom, you've got n degrees of freedom here, so at some level you should have n degrees of freedom here. That's in fact what you've got. Okay, they're like n kind of degrees of freedom, and then the whole second half of the spectrum is just kind of the copy of the first one. Okay, so no. I'll just say conjugate symmetry. But, okay, it turns out, okay, if we eliminate the redundancy in Z, okay, then the remaining variables are indeed IAD Gaussian, IAD circular symmetric Gaussian, okay? So the answer is Gaussian, on some level, you just got to be careful. It's complex Gaussian rather than real Gaussian, and moreover, you don't really have IAD across the entire vector. Okay, so here's the way to think about it, or a way to think about it. So Okay, we said this was the channel, right? Let me blow it up the way I did the x. Remember the x, we had the DC, and we had x1, and so on. We kind of decompose x into constituent parts. Let's decompose everything that way. Okay, so y has its DC. It has a vector I'll call y1. If n is even, you'd have an n over 2 sample. Let's do the odd case. So you don't have that. And then you have flip y1 star, right? Let me write that bigger. Like that. Yeah. So y, when n is odd, I can write y like that, right? Likewise, x, we had decomposed the same way. Question? No? OK. OK, so you have the DC gain of the channel. So it multiplies x0 to give you y0. You're going to have, this is a vector, so you're going to have the channel gains from frequency 1 up to wherever that ends. So that's going to be x, I'll call that lambda 1. OK, and then this is going to be lambda 1. I'm not sure what notation to use here. Tilde. It's going to be flipped. OK, so lambda, I need that for the noise, that space for the noise. Lambda 1 tilde is a flipped copy of lambda 1. Flip, I mean not the usual like transpose. Like you take a diagonal matrix and you make the last diagonal entry and make it the first and the first one the last. You take the matrix and flip it like that. Not like that, which is the usual transpose. Okay? These are all zeros. And Z I decompose the same way. Okay? All right. So I claim the decoder can just ignore this entire piece of the received signal. Why? Why can I do that? This is not intended to be tricky. Why is it safe for the decoder to just delete this? It receives this whole vector. First thing it does is just delete a whole bunch of samples. Why is that safe? It already has it, right? Like if you needed it, you could always get it back. Take this flip conjugate, you got it, right? So mathematically, we could say these two samples are a sufficient statistic for x given the whole thing, right? OK. Turns out, likewise, you can ignore this one too. That's a little bit more subtle. I'm not going to prove that rigorously, but the idea is the encoder is not going to put anything useful here, right? It's going to lock that at 0. OK. So there's no signal in that first the DC component. And we haven't shown yet that this is independent of this, but that turns out to be the case. And so the whole DC thing is just pure noise that's independent of everything, so not useful. OK. So the decoder can use this Y1 as the effective output of the channel. OK, in which case, the overall channel becomes a y1 equals lambda 1 x1 plus z1. Okay, and z1 has IID circularly symmetric Gaussian components. Okay, so we said z was not IID Gaussian because it's complex. It cannot be IID across the components because this is just a flip copy of that, so they're not independent. Okay, but it turns out if I delete this and I delete this, this part is indeed IID circularly symmetric complex Gaussian. I'll say components of Z1 are IID circularly symmetric complex Gaussian with variance n. Okay, so it'll be a homework problem again on a set that will be handed out a while from now. Okay. Note, if I only delete this, if I only delete these redundant samples, okay, I cannot have that the remaining ones are IID circularly symmetric complex Gaussian. You see why? Why is this vector not IID circularly symmetric complex Gaussian? What do we know about this one? Time domain signal is real, right? So what do I know about the DC? It's purely real, right? The time domain signal is real, the DC is purely real. Okay, so this has got to be purely real. This turns out to be a regular Gaussian, okay? This is not circularly symmetric complex Gaussian because it's purely real, okay? So, you know, it's kind of, it's messy on some level. Like this is a copy of this. This is regular Gaussian, this is complex Gaussian, okay? But if you peel away this part and this part, what's left is IID circularly symmetric complex Gaussian, okay? Any questions about that? That's 3. Let's do 1. So how do we do PAM when this is our channel? Y1 equals lambda 1, x1 plus z1. Okay, so let me write out this as at least the first couple samples. So take the 0 sample both sides. That's the first sample in this linear system, right? By the way, we start indexing y1 at 0, even though the 0 sample of y1 represents the 1 sample in y. Does that make sense? Okay. So like y1 0 is y1. You know, the first sample to appear in y1 is actually the sample 1 in y, because you're going to pad in the 0 for the DC in y. Okay. Okay, so the second sample in that equation reads as follows. You have y1, y1 equals lambda 1, 1. Sorry, lambda 1, 1, 1, x11 plus z1, 1, and so on. Okay, you get a bunch of these. Okay. So observe there's no ISI between complex samples, okay, in the sense that like any energy I put into x1 of 0 here, that's not going to somehow bleed into y1 of 1, right? That's just going to pass through right here, and it's going to not affect this equation at all. Likewise, energy from here doesn't penetrate back. Okay, you have just this pass through. Okay. So there's no ISI at the complex sample level. But ultimately, we want to encode bits and decode them, and we did that in the real world, or with real samples, not with complex samples. So you might ask, well, how are we going to do it here? So one thought, probably the first thing that comes to mind is, well, every complex number is like 2 real numbers, right? The real and imaginary part. So why don't we just like take the real and imaginary part of both the input and the output of each sample, and just like double the number of samples at our disposal? Then everything's real, and we know how to deal with that, right? We've done PAM when everything's real. So just treat this as 2x the number of equations, 2x the number of samples, by taking real and imaginary part of each input sample and each output sample. Okay, that doesn't quite work. It's a natural thought. It doesn't quite work. And here's the problem. So maybe I can describe it here even, like focus on just this first equation here, the zeroth, the one with index 0. Okay, so suppose you encode some bits in the real part and some bits in the imaginary part. Sorry, left arrow. Suppose I encode some bits here in this thing and some bits here. Okay. At the decoder side, you'll get y1, 0. It will have a real part and an imaginary part, like that. Clearly, I should use these two things to decode these two, right? Because the bits I send here are not going to somehow magically end up in y11, right? There's no ISI at the complex sample level, so it'll all be in y10, so it's got to be either here or here, right? Okay, the issue is, although you don't get ISI between complex samples, you get ISI between the real and imaginary component of one complex sample, i.e. bits I encode here could end up in here, and likewise here, right? If this was purely real, if y1, this is kind of hard to read, I'm sorry, if lambda, if this gain was purely real, okay, then signal in the real part of this sample would end up in only the real part of this one, and signal in the imaginary, purely imaginary part of this would end up in purely imaginary here, okay? But in general, it's not going to work that way. In fact, if this, suppose this thing is just j, suppose that's the gain, square root of -1, right? Okay, then you encode bits in the real part here, they end up in the imaginary part here, and vice versa. And in general, if you just have some arbitrary complex number there, both the real and imaginary part here are both going to be functions of both of these. So we've got mixing going on. We've got ISI on some level, okay, but it's not at the level of the complex samples. It's within one complex sample. The real and imaginary part are getting mixed together by the channel gain. Okay, so that's a problem, but there's an easy fix. So take the channel gain and just write it in polar form. Just write it as RK e to the j theta k. And then define a new output, y2, derived from y1, the kth sample of which is just y1 at k, with the phase of the channel undone. So times e to the -j theta k. Okay, so we're assuming the channel is known. So I can do this, right? If I know the channel, I know h, I know lambda. I know lambda 1, because lambda 1 is derived from lambda. So I can write lambda 1 like this. And then I can just take the phase off, pull the phase off, and undo it. And call this my new channel output. I've lost no information, right? If I want y1 back, I can get it by just multiplying by the phasor back. Okay, so no loss of information. The claim is this is a lot easier to work with, though, than this one. Okay, because y2 k okay, it's y1 of k with the negative phasor. So if you multiply this through, this is e to the -j theta k, lambda 1 kk, x1 k, plus e to the -j theta k, z1 k. All right, so I just took the equation that's boxed way over there and just multiply through by e to the -j theta k. All right, this now is exactly just rk, right? Because the phase cancels. Tell me about the distribution of this. took the noise and I multiplied it by this phasor. Exactly. Exactly, yes. All right, this is the circular symmetry of circularly symmetric complex Gaussian, right? So all I did was take the distribution, I rotated by theta k. All right, distribution's unchanged. Okay, so if you call this Z2 k, then what are we left with? You have just Rk, a real channel gain, x1k plus z2k. All right, so in matrix form, if we define, so let's write lambda 1 as lambda r times lambda theta, okay, where this is purely real, and these are just phase shifts. Okay, then y2 we can just write as lambda theta inverse times y1. Which is going to be lambda r times x1 plus z2. Okay, so we reduced our channel, our original channel, which involved time domain x and time domain y, down to this. Okay, and there are operations on the encoder side, there are operations on the decoder side. Okay, but once all those are in place, you reduce the channel to a channel like this. I now have real channel gains for each sample. My noise is circularly symmetric complex Gaussian. Okay, so now you can indeed decouple the real part and the imaginary part of each sample and just encode bits separately. Okay, so encode bits separately in the real and imaginary components. There's no ISI between complex samples. There's no ISI within one sample between the real and imaginary component either. Okay, because the channel gain is now real. All right. So this we can handle now. Okay, if you just take like real part of both sides and imaginary part of both sides, okay, you'll have then a bunch of real value channels. Okay, and with no ISI between them. Okay, and that we know how to solve. Right? You do your bit power allocation procedure. That's it. All right. There are a lot of steps in here, a lot of reductions. We don't have time for this now. I often put up a big block diagram that shows like each step end to end. Is it worthwhile to do that on Thursday? Okay, it'll be a little bit discontinuous because we're going to open with that, and probably by then a lot of people have forgotten all these steps. But anyway, so I'll go through that on Thursday, and we'll talk about how this compares to SVD. And then we need to bridge the gap from circulant H to Toeplitz H, right? And then once we have that done, we have two more things to do: unknown H and synchronization. And then we're good for labs 4 and 5, and we'll start talking about wireless. Okay, so we'll stop there, and I can kind of linger after class for a few minutes if you have questions about whatever. Otherwise, I'll see you Thursday.